All right. In the last lecture, I told you about equivalent capacitance for parallel capacitors, that is to say capacitors wired together side by side, as it were. A little later on, I'm going to be a little more definite about what I mean by parallel. But in any case, let me go through the second possibility, which I've already drawn on the board for you here. And I suppose this would be a good time to pause the recording. But first, this is the relationship I came up with in the previous recording. Parallel capacitors wired together will produce combined, or as we call it, an equivalent capacitance. And the superscript P here is just to remind you that we're talking about capacitors wired in parallel. And the equivalent capacitance is obtained mathematically simply by summing the capacitances of the individual capacitors that you've wired together in parallel. Again, very important to remember, this relationship is true only when all of the capacitors are wired together in parallel. Because there's another possibility, and that is this arrangement here, where the capacitors are said to be wired together in series. And I think I'm going to go ahead and give you a sense of what in the world that means. The names parallel and series refer to the behavior of the current as it flows. We do have a current, right, because charge flows from the top of the battery over to the bottom of the plate, so that's a flow of charge, so that's a current. Current is going to flow from the bottom plate of the bottom capacitor and around. So, and it is absolutely true, and please do remember this is very important, it is absolutely true that no single charge makes it around the entire circuit all in one go, because this is a break in the circuit, this is another break in the circuit. However, as you have seen in the lab, the circuit, at least for some time, acts like a complete circuit in the sense that you can light light bulbs and things, and so we'll investigate how that happens in some detail another time. But anyway, so if you could imagine, or if you chose to imagine something that is, I'm going to tell you, is just flat wrong, but if you chose to imagine that a charge starts at the top of the battery and made its way all the way around the circuit, then it would first hit this capacitor, and then it would hit that capacitor, first the top one, then the bottom one, as it made its imaginary way around. Again, I remind you, no charge actually does complete this circuit path, but whatever. Anyway, so the one right after another, that's what we mean by there's a sequence or a series of capacitors here. Okay, so one after the other. All right. And as for parallel, this will make more sense when I make that drawing again. But when the current flows in a parallel system, the current flows through all of the paths side by side. They flow parallel to each other. Anyway, we'll come back to that. Okay, so let's look at this arrangement here, and we're going to eventually talk about the potential differences that end up getting created. But let's first think about the charging process a little. Before I connect this, let's suppose we have a switch in here, at least temporarily. And let's suppose that at time 0, the capacitors are uncharged. Remember, that means that there's no net charge. They have plenty of charge. They just have equal amounts of positive and negative. Okay, so they're uncharged at t equals 0, and then I close the switch. We've talked about this before. Positive conventional charges will flow from the high potential of the battery, and they'll flow away. They'll try to drop to a lower potential, and the result is that. But let's think about charge rather than potential at the moment. That means the charges will find an escape route. Their mutual Coulomb repulsion will push them away, and they'll end up populating the top plate of this capacitor. If you want to think about it this way, the top of the battery is crowded full of positive charges, all repelling each other, and then as soon as I attach this top plate to the top of the battery, that gives them a place to spread out to. And so their mutual Coulomb repulsion, as I say, presses them out, and they end up populating the top plate here. But when that happens, the top plate here becomes strongly positively charged. Now, the bottom plate here, take a look carefully here, the bottom plate of capacitor C1 is not physically attached to the bottom of the battery. So the bottom plate, if it's going to get charged, if the bottom plate is going to get charged, and it is, the charge that it gets cannot come from the bottom of the battery because this bottom plate isn't attached to the bottom of the battery. Okay, well, it is going to get charged because, again, depending on how you choose to look at it, and since we're using conventional currents, we'll look at it the following way. The increasing positive charge on the top plate as the charging process continues, the top plate gets continuously more positively charged, and that is going to repel the positive conventional charges in the bottom plate. So the bottom plate is originally electrically neutral, so it has a bunch of conventional positive charges. Those get repelled downward as far away from the top, increasingly positive top plate as they can get, and so where do they go? They can spread out to this bottom plate here. Okay. Well, two things. One, the bottom plate, since you've pushed positive charges off of it, now has a net negative charge. And so the bottom plate of C1 ends up overall negatively charged, with a corresponding potential difference, by the way. Meanwhile, the top plate of C2 has now gotten positively charged, and it's going to repel positive charges from its bottom plate. And those, or if you prefer to think of it this way, the bottom, the positive charges on the bottom plate of C2 will fall to a lower potential at the bottom of the battery. Either way, you think, or both, frankly. And in any case, the bottom plate ends up losing positive charges and ends up with a net negative charge. And a few moments of thought should convince you that the magnitude of the charge on the other three plates must be exactly the same as the magnitude of the charge on the top plate of C1. Okay, so in short, C1 and capacitor C1 and capacitor C2 end up storing exactly the same amount of charge. Okay, so that's very important. So series, this is what I'm writing, series capacitors store equal amounts of charge. And when we ask about the total amount of charge that we stored, again, just like we did with parallel capacitors, we simply add however much charge is on this capacitor plus how much charge is on this other capacitor, how much charge is on C1 plus how much charge is stored in C2, and the total charge stored is simply the sum of those two. Okay. So the total charge stored is simply twice the charge stored on one of the capacitors. And so we'll say that they both manage to store an amount of charge that I will call Q. All right, well, what about the potential differences then? Well, there's two ways you can look at this, two ways you can think about this. One is you can say, remember, the general relationship, let me use a different symbol, Q. The amount of charge you could store on a capacitor is C times V, right? And in this particular case, both for these two different capacitors, their capacitances are different, but the amount of charge they're each going to store is going to be the same, which implies that the potential difference across the capacitors must be different. In other words, delta V here is different from delta V here. Delta V across the top, the delta V across C1 is different from the delta V across C2. So just because of properties of conductors, since the top plate of C1 is connected to the top of our battery, the top plate must be at potential what I'm going to call V sub A, the bottom plate of C2 down below has to be at the same potential as the bottom of our battery, which I'm calling V sub B. Okay, and so the potential difference across both capacitors combined is VA minus VB, but what about across one of the capacitors one at a time? Well, that's not difficult. Again, potential is constant over a conductor, no matter what the conductor looks like. And if you look at the middle bit here, the top plate of C1 is electrically connected to the top plate of C2. The bottom plate of C1 is electrically connected by this wire to the top plate of C2. So from the point of view of the charges, those two things combine to be just one single conductor, which means that whole thing is at the same potential. This whole middle bit is not at potential VA, nor is it at potential VB. So it's at some middle potential, because it's in the middle of the pack there. Let's call it V sub M, I guess. Okay. So now we can do the calculations that we want to do. And what calculation do we want to do? Well, I'm going to pretend that I'm going to ask the question, how much charge can we store? The real question I'm going to ask is, what is the equivalent capacitance of this arrangement? All right, so let's take a look at it. All right. So again, my argument is, since the charge stored, we'll call that capital Q, since the charge stored is the same for both of these series capacitors, but their capacitances are different from each other, that means the potential difference across each capacitor must be different. So that means, let's see, the potential difference, let's start with C1. The potential difference, which I will call V1, is VA minus VM, but the charge that we can store in that capacitor can be calculated as Q, same Q for both capacitors, I don't need a subscript there. Q is equal to C1 times V1. Okay. Across C2, on the other hand, the potential drop is VM minus VB. Please notice the ordering of VA, VM, VB in these various equations. Okay. And the charge stored, again, Q, can be calculated as C2 times V2. All right. Now, across both capacitors, the total potential difference from the top of C1 to the bottom of C2 that's easily calculated. We'll just call that V, and that's going to be VA minus VB, which if I solve this for VA, solve this for VB, subtract them, it's not easy. It's not hard to see that this is going to be V1 plus V2. Okay. But we just saw that V1 is related to the charge stored in capacitor C1. So from over here, V1 is equal to Q over C1. V2 is equal to Q over C2. And so if I combine these three equations together, I find that the total potential drop can be written as V1 plus V2, but V1 is this, Q over C1 plus Q over C2. Okay, so far so good. We're almost there. Now, if I define C equivalent to be such that the charge stored in one of the capacitors divided by the potential drop across both capacitors, so that gives me, rather trivially, that the total potential drop is Q over C equivalent, I end up with the result that, and this is what I was actually after, of course, the equivalent capacitance of the two series capacitors is, so V is Q over C equivalent is equal to Q over C1 plus Q over C2, and so the relationship that I develop is that the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of C1 and of C2. Okay, so we have a reciprocal relationship here. And then finally, once again, I can generalize this argument to an arbitrary number of capacitors wired together in series. And we find that the reciprocal of the equivalent capacitance is the sum of the reciprocals of the individual series capacitors, and I will put the superscript S's there to make it clear that we're talking about series. Okay, and that's the other relationship. It's not terribly difficult. It is, however, a very it does carry with it lots of very common and unnecessary mistakes. And in the next recording, I'm going to do for you some examples which are mathematically simple, but conceptually they're a little challenging. And I'm going to point out for you some common places where common errors are commonly made, and how to avoid them.